Okay, the first thing we're going to do here is run through the first four from the worksheet here that you're going to get in a minute that you had to do over this weekend. And so what we were looking at were these trig equations here where they were in a quadratic form. So if you notice, like on the first one, we have a sine squared there and a sine. And so with that square there and that sine there, we get this quadratic form. So the idea is just like with quadratic equations, a good way to solve them is to factor them. Okay, so on numbers 1 and 2, in both cases here, you could factor out a sine theta. So let me factor out now sine theta. And so that would leave me with square root of 2 times sine theta plus 1. Okay, so it's like a common factor of sine theta. And now we've got equals 0. And so we're going to use the zero product rule here and use this is the A, this is the B, and we have them equal to 0. Well, if A times B equals 0, then A could be 0 or B could be 0. Okay, so all we have to basically do now, since it's set equal to 0, is set both factors equal to 0. So now we're going to get sine of theta equals 0, and then square root of 2 sine theta plus 1 equals 0. And now we're going to solve both of these in this just for the interval from 0 to 2 pi. And so the first one is basically already solved for. It's already sine is already isolated, so we're going to check on our unit circle here. Let me get a unit circle going here. So my unit circle, if I look here where sine is 0, so that's where my y coordinate here is 0. And so that would be there at 0 and at pi. So we'll get theta here to be 0 and pi. Now, let's look at our other part of the equation here. Now, this one requires a little bit of isolating, unlike that other one here. So we're going to have to subtract the 1 over. So we'll get square root of 2 sine theta equals -1. And then we divide off the square root of 2 on both sides. We get -1 over the square root of 2, which if we isolate that here, that would just be negative square root of 2 over 2. And so we're going to find, well, where is sine negative square root of 2 over 2 on our unit circle? So let's take a look. So let's see, where is sine negative square root of 2 over 2? Well, sine is negative in the third and fourth. So notice that's going to put me here at 5 pi over 4 and 7 pi over 4. And now we get theta is 5 pi over 4 and 7 pi over 4. So notice we have 4 solutions to the equation there. Okay, now the next one is real similar. It wasn't actually as difficult here. So let's see the same idea. It's a quadratic form, and what we can do here, they have a common factor of a sine, is we can factor out a sine. So we're going to get sine theta times, now that will leave me with 2 sine theta minus 1. Okay, so now using the zero product rule again, that means both of these factors could be 0. So we'll get sine to be 0, and then 2 sine theta minus 1 equals 0. So again, where is sine 0? Same thing as it was on the last problem here. So same two solutions. Sine is 0 at 0 and at pi. Okay, now my other one I'm going to have to isolate a little bit. So I'm going to have to add the 1 over. And then we divide by 2. And so we get sine theta equals 1/2. And so we can check on our unit circle here. Where is the sine 1/2? So let's see, we're going to get sine here is 1/2 there at pi over 6. And let's think, where else is sine positive? Sine is positive in the second quadrant over here too. And so sine is also 5 pi over 6. So pi over 6 and 5 pi over 6 are the other two solutions. Okay, so both 1 and 2 there, you factored out a common factor. Now, on numbers 3 and 4, these were also, again, a quadratic form, but they required a different kind of factoring. So again, they have this trinomial feel to them here, because in this case, we had both of those here, the constant in the end. So we said the easier way to kind of go about these was to make a substitution. So instead of trying to factoring with the trig functions in there, what we're going to do is we're going to let A be equal to the sine of theta. And so it's going to make it a nicer looking equation. So that would change this instead of 2 sine squared theta, this would just be 2a squared plus, and there again, sine theta is just a, minus 1 equals 0. Okay, so now it's just an easier kind of quadratic to solve here. So notice it does have a leading coefficient, so we're going to multiply the ends. 2 times 1 is 2. Factors of 2 that subtract to give me 1 would be 2 and 1. And there again, since this has a leading coefficient, I have to split this. Okay, signs will be different. It'll be plus 2a minus a. So we're going back again to some old algebra 2 with quadratic equations here. Now I've split it. Now let me group it here. So out of my first group, I could factor out a 2a. This will leave me with a plus 1. Factor out a negative 1 in the second group, and that'll leave me with a plus 1. And so now it'll factor to a plus 1 times 2a minus 1. Okay, so our solutions here for a is that a would be negative 1, and a would be a positive half here. Okay, now we're going to have to go back. And so those are my sort of my algebra solutions. Now what I need are my trig solutions. So recall here that a was equal to the sine of theta. So let's make that substitution back into it. So we have sine of theta equals negative 1, and then sine of theta equals 1/2. So let's check on our unit circle. Where is the sine negative 1? So let's see. The sine is negative 1 down here at 3 pi over 2, and that's the only location there. So just one solution for that one. So we get theta is 3 pi over 2. And then where is the sine of positive 1/2? That's actually the one that was just like we did earlier. And so that's at pi over 6 and 5 pi over 6. Okay, now for number 4, sort of the same idea here. It's another quadratic sort of type trig equation here. And so we're going to make that substitution again. And we're going to let a be equal to the sine of theta. So that's going to turn this equation into 7a squared plus 16a plus 9 equals 0. And again, with the quadratic, we can solve these by factoring. Now again, we have to multiply the n terms and split the middle since we have a leading coefficient there. So 7 times 9 would be 63, and factors of 63 that add to be 16. And let's think about that a minute. So again, I'm looking for factors of 63 that add to be 16. And so let me list factors of 63 to kind of figure that out. So you have 1 and 63 there. Those would not give me 16. Um, let's see, 3 times 21. 21 and 3 would not give me 16. Let's see, we could try 7 times 9, and that's worked. Okay, so our factors would be 7 and 9 here, so we're going to split 7 and 9. Both of them would be positive. Okay, now let's group them in factor. So out of my first group here, I could factor out a 7a. That would leave me with a plus 1. In my second group, we can factor out a 9. That would leave me with a plus 1. And so now we'll get a plus 1 times 7a plus 9. And so our solutions here for our a equation, we'll get negative 1 there. Let's see, that would give me 7a equals negative 9, so a would be equal to negative 9 over 7. Now let's recall, we would say that a would be the sine of theta. So we'll get sine of theta equals negative 1. Now look what's going to happen here on this one. We get sine of theta equals negative 7, or excuse me, negative 9 over 7. Well, negative 9 over 7 does not fall in between negative 1 and positive 1. And then we talked about the range of the sine graph here. That sine curve bounces back and forth between negative 1 and positive 1, and that number does not fall in between that. And so just to kind of illustrate that, if you wanted to see here, you could punch in on your calculator the inverse sine of negative 9 over 7, and it would give you an error. So basically, this part of the equation doesn't lead me to any real solutions. So we only have this one part here where we have sine of theta equals negative 1. So let's look on our unit circle to where sine is negative 1. So I'm looking for the y coordinate to be negative 1, and that's down here. They're getting it 3 pi over 2. So we only have just one solution there for this equation, just 3 pi over 2. Okay, now you'll have some more of these to do, which is basically from 5 through 9 that I want you to try out there. And let's look here at one additional topic. Now we're still going to solve more trig equations, but let's look at an idea of maybe how I can do that in a different way here. So let's look at this one, and then I'm going to lead you into sort of the topic here. So let's say we have cosine squared theta equals 4 times the sine of theta minus 1. Okay, so if we look at this, we see it does have a quadratic feel to it. You've got a cosine squared, but we have sort of a big issue. And this big issue is this has a cosine squared and a sine. And so that creates a problem with solving it. And so, if I only have cosines or if I only have sines, even if we have square ones, we've talked about we could set them all to 0 and factor them. Okay, so we've got a problem with this. So the key here is to figure out, well, how can I change these so that they're either both sine or both cosines? Now, the hint here is to look at this one, and we should see something about that one being squared that we can take an advantage of. And so I'll give you a minute to see if you can think about that. What's something I could put right here for cosine squared here? So I could write it in terms of sine instead of cosine squared. Okay, here's the big idea. This is what we're going to use. a Pythagorean identity. Okay? And so this is sort of the title for today's lesson here, is we're going to solve equations using Pythagorean identities. So what we're going to see in all these problems today is we're going to have sines and cosines. And so what the idea is there's going to be probably one of them that's squared, and we can use a Pythagorean identity to make a substitution. So let's look how we're going to make this substitution. Now, we're only dealing with sines and cosines, so the only Pythagorean identity here that we have to look at is our very first one that we should know really well here, that sine squared plus cosine squared equals 1. And so what I want happen here, in other words, kind of look, this one's not squared, so I really can't do anything with that one. But the cosine squared one, what I can do there is replace cosine squared in terms of sine. And so notice, if we solve our Pythagorean identity for cosine squared, we would get cosine squared theta equals 1 minus sine squared theta. And that's our key right there. So for that cosine squared, I can replace that with 1 minus sine squared. So it's a Pythagorean identity and using that substitution right there to solve this equation. Okay, so let's watch this happen. So instead of writing cosine squared right there, we're going to write 1 minus sine squared because it's the same thing. So we have 1 minus sine squared theta equals, and I'm probably going to do what most of you think we should do on the right side, and that would be to distribute and get rid of those parentheses. So this will give me 4 sine theta minus 4. And so now what we've got is what I wanted in the beginning, is I only want an equation that had sines, and not sines and cosines. Now notice it is a trig form, so we're going to set it equal to 0 to solve it. Now, notice the negative sine squared's on the right side, so I can get it to a factoring form. I'm going to put everything over on the right side and set it equal to 0, because there again, if I factor, it has to be set equal to 0. So negative sine squared is going to go over to the right side and just be sine squared theta. And now we'll have plus 4 sine theta. And now I got to bring my 1 over here also, so I'm going to subtract 1 from both sides, and so that'll give me negative 5. Okay, now we're sort of back to what we were kind of starting on from Friday. It's just a quadratic form, and so what we'll do is we'll let A be equal to the sine of theta. And so I'm going to use a little A equation here, so that would be A squared plus 4A minus 5. And now factors of 5 that subtract to be 4 would be 5 and 1. Right? And notice, I don't have to split this one here. I didn't have a leading coefficient, so it wasn't necessary to split 4A. All right, signs are going to be different, and it'll be plus 5 and minus 1. So now we'll get A to be equal to negative 5 and A to be equal to positive 1. Now recall, we let A be sine of theta here. And so we're going to get sine of theta equals negative 5 and sine of theta equals 1. Now notice with negative 5, that doesn't fall in my range from negative 1 to positive 1. And if we punch in inverse sine of negative 5 on our calculator, that's going to give us an error. So that one doesn't lead to anywhere. Now we're going to look back, well, where is the sine of positive 1 on my unit circle? So that's the y-coordinate being a positive 1. And that only happens at one spot there. So if you look that up, this should be pi over 2 is where sine would be 1. Okay, now let's take a look at another one here. You might not have caught on to that one just yet, and that's okay. I'm going to do a couple more here for you. And by the way, let me kind of give you a reference here. On your trig equations 3 worksheet, this one is very, very similar to number 12. Okay, so if you want to jot that down in your notes here, when you get to number 12 in your homework, you could certainly use that. Now, I'm going to do one sort of similar to the one we just did here, and it's going to be a lot like number 13 in your homework. Okay, it'll be a little bit different though. So let's take a look at this one. So we have here cosine squared theta equals 7 times sine theta plus 1. So it's really, really similar to the one I just did. So let's see if we can maybe catch on a little bit better this time. Now, so here again, the idea is we have a cosine squared and then a sine. And so the main goal here of what I want to do is I want to make this an equation that only has sines or it only has cosines. So again, I'm going to make a Pythagorean substitution for that cosine squared right there. So cosine squared, according to my Pythagorean identity, should be equal to 1 minus sine squared. So I'm going to substitute right here 1 minus sine squared theta. Okay, now I'm going to distribute out the other side. So we'd have 7 sine theta plus 7. Okay, so now take a step back and look what we've got. We had an equation that had a cosine and a sine. Now they only have sines. Now granted, one is a sine squared, but we can just make it into a quadratic form. So since we're going to make it in a quadratic form again, we'll set it equal to 0. And notice because that's negative right there, we're going to put everything on the right side. So that'll be a nice positive sine squared when we move it over to the right side. So it'll be sine squared theta plus, we'll bring down that 7 sine theta. Now, we also need to take this one over, and so that's going to give me a positive 6. Okay, very, very similar to this last example now. And so, again, here we could switch it to an A form so that it's easy to look at and factor. So we'll let A be sine of theta. So this will be A squared plus 7A plus 6. And now factors of 6 that add to give me 7 would be 6 and 1. There again, it doesn't have a leading coefficient, so I don't have to split it. And so now we'll get A to equal negative 6 and A to equal negative 1. So recall that we let A be sine of theta. So we'll get sine of theta equals negative 6, and then sine of theta equals negative 1. So sine of theta equals negative 6 is not going to give me anything because that doesn't fall in between negative 1 and positive 1. But sine of theta equals negative 1 is, and so I'll look up on my unit circle. So where is the sine equal to negative 1? And that would be at just pi. So my solution there is just pi. Okay, let's try to look at it, at least 2 more here. Okay, now what I'm going to look like, or what I'm going to look at, excuse me, is one sort of similar to number 11 as to what you'll get here. Okay, let's try this one. Let's say we have 3 plus 3 sine theta, or excuse me, I meant to say here cosine theta is equal to, and let's say 2 times sine squared theta. Okay, so there again, what we really want to do with this is we want to make this into an equation that only has either sines or cosines, but not both sines and cosines. So with this one being squared, we're going to take advantage of that. And so we can write that in terms of cosines by using that Pythagorean identity. So sine squared, think about that a minute. I'm going to bring down the 2, okay? And now we're going to distribute that 2 for whatever we put in there for sine squared. So let's see if you can think just a second. What can we substitute for sine squared so we can match it up with that cosine right there? So by our Pythagorean identity, for sine squared, we could put right here 1 minus cosine squared. Okay, and so now this equation is only going to have cosines in it. Okay, so now let's distribute the 2, and then we'll see where we can go from there. So this will give me 2 minus 2 cosine squared theta. And there you notice I'm not really doing anything on the left side. I'm just working all this right side stuff. Now, so what we've got is another quadratic form here. We've got a cosine squared and a cosine. So what we want to do is we want to set that equal to 0 so we can factor it. So since this one is negative, let's put everything on the left side. Okay, so you have to watch real carefully. The negative 2 cosine squared theta is going to go to the left side, so that's going to make it positive. So it would give me 2 cosine squared theta. Let's bring down this 3 cosine theta. Notice it's not changing to minus here because I'm not switching sides with it. And now we're going to subtract 2 from both sides. And so that's just going to give me a positive 1. Okay, so basically what happened there is we moved everything over to the left side so it could equal 0. Now, let's change it to an A form here so we could factor it easier. So this would be 2a squared plus 3a plus 1 equals 0. And now this will factor fairly easy. Now this one does have a leading coefficient, so we'll have to split the 3a. So 2 times 1 is 2. Factors of 2 that add to give me 3 would be 2 and 1. So this would be 2a and 1a. Both signs would be positive. So now let's group it here. Out of the first group, we could factor out a 2a, and that would leave me with a plus 1. My second group, just factor out a 1. That would leave me with a plus 1. And so now we'll have a plus 1 times 2a plus 1. And now let's solve. So we'll get a here to be negative 1. And then a would be equal to negative 1/2. Now recall, when we made a substitution back at this step, we said a would represent the cosine of theta. So we'll have cosine of theta equals negative 1, and cosine of theta equals negative 1/2. So now let's look on our unit circles. Both of those are actually going to give me some good solutions there. So where is the cosine negative 1? And so that would be at pi. Okay, and I believe that's the only solution there. Now, where is the cosine negative 1/2? So that would be at 2 pi over 3. And so cosine is also negative in the second quadrant, so it would also be 4 pi over 3. Okay, and that kind of makes me wonder, I'm going to look back at the question before here. We had sine theta equals negative 1. That's wrong, I believe, right there. So sine is negative 1. It kind of reminded me here when I just did that problem that I don't think I had that right. So let's fix that. The sine is negative 1 at 3 pi over 2, not at pi. I was thinking where cosine was negative 1. That was incorrect. So that should have been 3 pi over 2 there on that previous example. Sorry about that. Now, let's take a look at one more here that I want to do for you, and then I'm going to sort of let you have one to kind of practice with. Let's try this one. So we have 6 minus 6 times cosine theta equals 4 sine squared theta. Okay, so I hope you're catching on here kind of by now. What we're doing is we're going to substitute something in there for sine squared theta that should be written with a cosine. That way all we'll have is just cosines in our problem, and we can set up something with factoring. So for sine squared, what we can do is substitute 1 minus cosine squared for that. Now notice we have the 4 in front, so when we make the substitution, all we're going to do with the 4 is just distribute that. So for sine squared, we're going to substitute 1 minus cosine squared theta. And so that's using that, again, that Pythagorean identity to make that substitution. So now all we have is cosines. Now, let's distribute the 4. So this would be 4 minus 4 cosine squared theta. Okay, now that we've got everything kind of expanded out and everything is with cosines, now let's set it equal to 0 here. So since this one is negative, let's pull it over to the right side so we can make it positive. Okay, I'm going to bring down minus 6 cosine theta. And now I'm going to bring the 4 and subtract it over on both sides, mainly to the left side here, so that would leave me with a positive 2. And now it's set equal to 0. So now it's set equal to 0, let's sort of switch to an A form here. So this will give me 4a squared minus 6a plus 2 equals 0. Now, you may hear probably say 4 times 2 is 8, and factors of 8 that add to give me 6 would be 4 and 2. And that would certainly work. Now, you may notice here that there's a common factor of 2 that I could get out. So I'm just going to divide that out, and that'll make it easier. Now, that would be something that you would not have to do, but there again, it does make it a lot easier. Okay, so I just got out a common factor of a 2 there. Now, let me paste this over real quick. Okay, so now let's look for factors of 2 that add to give me 3. That would be 2 and 1. See, both signs would be negative. So out of the first group here, we'll factor out a 2a. That'll leave me 2a times a minus 1. And then factor out a negative 1. So that'll leave me with a minus 1. And so now we'll have a minus 1 times 2a minus 1. So we'll get a here to be 1, and then a to be a positive 1/2. Okay, so now let's recall here. Let me go back. What did we let a be? So we assign a to be the cosine there of theta. So we'll have cosine of theta equals 1, and the cosine of theta equals 1/2. So now let's look, where is the cosine 1? And so that would just be one solution for that one there. That would just be at pi over 2. Just looking on my unit circle there. And so where is cosine 1/2? And so that would be at pi over 3 and 5 pi over 3. Okay, now that we've seen some now, let me give you an example here to sort of try. All right, so let's see if you can do this one. So we have 9 times 1 minus sine theta is equal to cosine squared theta. Okay, so at this time, somebody pause the video here for about 3 or 4 minutes to see if you guys can try to get the correct answer here. All right, so pause the video. Okay, so let's see how we did on this one. So for cosine squared, here what we should have done was made the substitution of writing here 1 minus sine squared. And so now our equation only has sines in it. instead of a cosine and a sine. Now, hopefully you distribute it on the left. So it'll give you 9 minus 9 sine theta. Now, let's set it equal to 0 since it's a quadratic form. So this one's going to add over, and so we'll make it positive. So it would be sine squared theta. Now we'll bring down minus 9 sine theta. Now let's bring this 1 over, and so that will give me a positive 8 there. Okay, and let's notice that this will factor real nicely. You didn't even have to split it here because it didn't have a leading coefficient. Let's probably switch it to the A's here. And you may be to a point here, once you get used to doing these, you can actually do these equations here without making that A substitution. Some people could factor with just the trig in it, and that's fine. Now, factors of 8 that add to give me 9 would be 8 and 1. Okay, both signs would be negative. So we would get A to be 8 and A to be 1. So recall what we're letting A be is sine. So we have sine theta equals 8 and sine theta equals 1. So that's not going to lead me to anywhere because 8 is not in between negative 1 and positive 1. Now, on our unit circle, where is the sine equal to 1? And so that would be at pi over 2. Okay, now you should finish here for me from trig equations 3, right, which you should get sometime here. Numbers 5 through 16. All of them will be quadratic-like. You want to make a note on it here, 10 through 16, which you guys don't have to do 10, so that would be 11 through 16. You're going to use a Pythagorean identity and to make a substitution to solve those.